This lesson is about vectors, and here are your objectives. So a vector is a quantity that has size or magnitude and direction, whereas a scalar is something that has magnitude only but no direction. Let's look at some examples to help clarify that. So vectors include things like force and velocity, acceleration, displacement, and momentum, all of which have both magnitude and direction. Whereas scalars, things that have magnitude or size only but no direction, include things like length, mass, speed, and energy. Now, because vectors have a direction, we can represent them with arrows, where the length represents the magnitude and the direction the arrow is pointing represents the direction. Let's talk a little bit about how we can manipulate vectors. First, we can translate vectors or shift them around without changing them in any way. So if this is the vector A, then moving it over here, as long as it has the same length and direction, it's still the vector A. We can multiply vectors which have magnitude and direction by scalars which have magnitude only. So for example, if this is the vector A, the vector 2A would have the same direction but double the length. Something like that, perhaps. By the way, sometimes you'll see vectors drawn or written with a bold letter instead of a letter with a little vector arrow over top of it. Negative vectors have the same magnitude but opposite direction. So we can turn a vector around just by putting a negative sign in front of it. So if this is the vector A again, then if I draw it with the arrow pointing in the opposite direction, that's the vector negative A. We can also do arithmetic calculations with vectors. So to add vectors, we place them head to tail, where this is the head, where the arrow is, and this is the tail, where there's no arrow, and we join the beginning of the first to the arrow of the last at the end. I'll show you what I mean. So when we add vectors, we call the sum the resultant. So here's vector A, here's vector B. If I were to add them together, I'm going to put them head to tail. So I'm going to draw A like that, and then I'm going to draw B like that, where the tail of B is at the head of A, and then I connect the two of them. So the resultant goes from the start to the very finish like this. So that vector would be the vector A plus B. Okay, let's do it in the other order. If I do B first, and then at the head of B draw A, then I get this. And notice that if I've drawn them carefully, the resultant of B plus A is the same as the resultant A plus B. So when you're adding vectors, order doesn't matter, just like when you're adding things arithmetically. Let's talk about subtraction. To subtract a vector, you add its negative. So A minus B is the same as A plus negative B. Remember, we can make a vector negative by flipping it around. So if we use the vectors above, then A minus B is A, like that, and then negative B would point upwards. So that's negative B. Therefore, A minus B is that vector there. Okay, let's do it in the other order now. B minus A, so B would look like that, and negative A looks like this. So now notice that if we're subtracting vectors, order does matter. B minus A has the same magnitude, but opposite direction from A minus B. Last, let's talk about resolving vectors into components. We can break down or resolve a vector into perpendicular components, and this becomes really important when we're talking about motion in 2 dimensions. So let's imagine that we have a force at an angle that should say theta, a force at an angle theta from the horizontal. So this is my horizontal, and I want to break it down into components, meaning I want to figure out what 2 perpendicular vectors, if one was arranged like this and one was arranged like that, would add to give this vector. I'm going to call this f sub x and this f sub y. By the way, notice that f sub y could also be drawn here on the axes, like that. Now, if we look at this right triangle, then cos of theta is equal to the adjacent side, f sub x, over just plain old f. Solving for f sub x, we get f cos theta. This is the horizontal component. This is the horizontal component of the overall force x. So we've just solved for f sub x. It's equal to f cos theta. If we look at the sine function of that angle theta, sine theta is equal to opposite f sub y over f. And again, now solving for f sub y, we get f sine theta. So the length of this component is f sine theta. This is the vertical component. So that's how you decompose these into components. I often remember that cos collapses the hypotenuse of the right triangle onto the side. So cos collapses if this is the angle I'm collapsing this way, and sine swings me away from the angle in that direction. That's just a little mnemonic that I use. So that's resolving vectors into components. This actually gives us another way of adding vectors. Let's say we wanted to add this vector and that vector. One way of doing it would be to resolve this vector into its components, which I'm drawing in blue. This one already only has a horizontal component, so I resolve the vectors into components, and then I join them tip to tail. Now here it's easy to see that the resultant of the black vectors is the same as the resultant of the blue vectors, but that illustrates that when you add the components of vectors, you get the same as if you added the vectors themselves. So that's an introduction to vectors.